Ce qu'on a appris, c'était prérequis de cryptographie quantique. On est en train de finir ça aujourd'hui. On va finir, certainement. Même ça va durer 2 heures. Il n'y a pas de souci. Je ne m'inquiète pas. Alors, absolute value of a complex number. Consider a complex number. And I'm going to just write the things that we learned. And this is the absolute value. See, it's defined such as and it's for a complex number. And then we define this with 2 vectors. And then we define this pure state of qubits can be pure state. I love these things, it's so beautiful. And standard basis, then we have Hadamard basis, multiple qubits, EPR pair, and now is combining qubits using the tensor product. That's what we're gonna do today. What is a tensor product? It's related to dimension and augmentation of dimensions of a state, of a quantum state. And this is my. So far, we learned how to represent the state of 1 qubit, of 2 qubits, and more generally of any number n of qubits as these 2 to the n dimensional vector. Why? Because this x, like 0 or 1, this has 2 dimensions, right? It's 2 to the 1. When you do this, it becomes 0, 0. It's like combinatorics. And it's 2 and 2. So it's 2 to the 2. You have, this is the numbers, 1, 1, 2. So if you have 3, it's going to be 2 to the 3. It's like 2 and 2 and 2. It's not music, it's quantum. It's 2 to the 3. So it's 2 to the n dimension. This normalized vector can be expressed as a linear combination of and be the string. Let us now imagine that we have 2 qubits A and B, and we can write the state of qubits in complex vector states squared, and the state of qubits respectively. How can we find the vector that represents the state of both qubits at the same time? When talking about multiple qubits, we will often refer to A and B as systems or registers. These words are used interchangeably to designate abstract quantum systems which could represent quantum systems in different physical locations. When the 1 qubit corresponds to the quantum system built in different parts of Alice, that's it. We will use, I'm going to get the marker. Let's wait a minute. If I can find it. Yeah, I found it. The highlight marker. And I'm going to highlight it. We will use AB to denote the joint quantum system consisting of the qubits, and in general we will use subscript. Kronecker product or tensor product? So, what is it? I want to write these two systems together, joint system. But what is a joint system? Just like it has real life applications in the experimental quantum computation. 0 is 1, 0. This is the vector. This is the system A, tensor product, system B. Both of them mathematically are the same, but they have different meanings because they're belonging to different systems. So, for example, psi A is equal to what? Alpha A, 0A, plus beta A, 0, 1B. 1A. Sorry, 1A. Yeah. And this is phi B. I don't know why they chose phi, but it's okay. Phi, you can choose psi B too. Psi B2, but it's okay. Alpha B, 0B, plus beta B, 1B. This is belongs to C2. This A, this belongs to CB. It's not A and B, it's just C. Yeah, C. And is equal to alpha A, beta A, and this is equal to alpha B, beta B. So the tensor product of these two states is defined like such this. This is what? Alpha A, beta A equal to, comes in, alpha A, beta A, beta, equal to alpha A, this goes here, alpha A, alpha B, alpha A, beta B, beta A, alpha B, beta A, beta B. For vectors psi 1, the tensor product is a vector is this, given by this. Okay. Because I love this, I'm gonna write the general form, otherwise it's kind of limpide. It's clear what is it about. So psi 1 and psi 2, D1 and D2. So this is psi 1 belongs to C, D1, and there's psi 2 belongs to psi D2. And the tensor product belongs to the multiplication of these two. Not multiplication. I was wrong. Tensor product. But this is just not complex numbers, so it's the state. Well, it's a state vector, so it's complex. It's a tensor product. Yeah. So this is gonna be what? This gonna be what? Alpha 1, D1, alpha D, alpha D, gonna write psi A psi B equals to psi A psi B. You want to say 0 A 0 B equal to 0 A 0 B equal to 0 0 A B. Combining several identicals, combining several identical states. Distributivity. This relation holds not only for Kessel, but also for the bras. Psi 1 over psi 2 plus psi 3 equal to psi 1 psi 2 plus psi 1 psi 3. Then the other side is the same as psi 1 plus psi 2 plus psi 3. Tensor product is not commutative. This is works for the cats and the bras, both of them. Distributivity and also associativity, but they're not commutative. In other sense, necessarily psi 2, psi 1. Very interesting. This is wrong, the writing. Combining several identical states was this. These were several identical states in different systems. Right? So this is going to be psi n. So what I wrote, it was a mistake. I wrote psi 1, not psi 1 here. This is different. Psi 1 here is a different state than these ones. Psi 2 plus psi 3. This is going to be psi 1, psi 2 plus psi 1, psi 3. Tensor product. But if it was outside, that was a different state. That's a different thing. It would be psi to the 2 plus psi 1, 2 plus psi to the 2, 2, 3. Could we, the question is, can we add this and write 2 psi to the 2? If I put out the numbers out of the bracket. Question. I don't know the answer, I'm going to think about it. The answer is no, because the systems are different. Systems 1, 2 is different from system 2, 3. This is my perception. It could be different. And this is wrong, I think. This is equal. But this is not equal. Because there are two different systems. Wait, two different states. There are two different states in different systems. This is not equal unless these are equal. Then this is equal. Construct an n qubit space out of 1 qubit using tensor product. I'm gonna highlight this because it's important. A basis for the space of n qubits So recall that the standard basis for 2 qubits A and B is given by zero zero AB, 0 1 AB, 1 0 AB, 1 1 AB, 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 AB. 1 0 0 0, 0 1 0 0, 0 0 1 0, 0 0 0 1. One zero, okay. So A and B. For example, this. How do we get this? This is equal to 1 A, 0 B, equal to 1 equal to 0 0 B 1 equal to 0 0 1 0 8. The problem that they have is, where does the prefix A go here? I don't think you need to write this here. You need to write here AB. So this is a wrong notation to put B here. There's no A here. So A goes where? That's the question that they have. The notation and writing. Okay. Told you I'm going to solve all the questions. I'm going to do that. Consider states plus The joint state is A and 1B. Okay. And the B is, state B is 1B. That's all. 1B. States AB is plus A B. Simple, right? 1 AB plus 1 AB. 2. So if we do plus B equal to 0 plus 1 B square root of 2, then B is 0 0 AB plus 1 0 AB plus 0 1 AB plus 1 1 AB over 2. They asked us, this is a pure state over 2, which is this gonna add up to 1 1 1 1 over 2. But we have been asked in quiz 1.31, is this a pure state? The answer is no, because it's not normalized. It's a very simple question that they ask in the quiz, and the answer is no, it's false. And these are two different state qubits in different states. They're not the same, so this is not going to be equal to phi transapodic psi. And it's very easy. You put 0 1 1 0, they're not equal. This is going to be 0 1, which is 0 1 0 0. That's going to be equal to 1 0, which is 0 1 0. Simple as that. Okay, I'm getting a little bit tired, but I need to go forward. Okay, pause. It's not very challenging. It's extremely beautiful written, but it's not that much challenging because it's just like I've done this like 12, 13 years ago. But it's okay. Consider two qubit states. Psi. How do you write this in the vector form in the standard basis? In other words, compute a psi. Okay, let me write. These are very easy questions, and I love it. But you need to go to a higher level too sometimes. challenging states. So, okay, 0, 0, psi is going to be equal to alpha 1, alpha 2, alpha 1, beta 2, alpha 2, beta 1, beta 1, beta 2. It's going to be the option number C. Consider the following states psi of 2 qubits, where psi minus is written in the standard base. The right written in the standard base statistic can be expressed as, okay. It's very simple. It's like, Hadamard basis. You want to write Hadamard basis in the computational standard basis, and I want to know that what is the notation? What is the this is the 2 state that we have, A, B. It's going to be minus, minus. And it's going to, minus is 0, 1, equal to tensor product, minus 0, 1, square root of 2. I say radically because it's French, and it's to use it in Persian too. 0, 0, minus 0, 1, minus 1, 0, plus 1, 1 over 2. So that's it. And so it's false, because the one that we have in the here is minus 1, 1, but it's not minus 1, it's plus 1, 1. Minus, minus. Minus, minus is plus. Minus 1 is minus, minus, plus. Simple as that. We can't just say that 1, 1, 7, 2, 1, it turns out it's the case. So every joint state cannot be separated in two separate quantum states. The tensor product is called entangled. Of course. Necessarily doesn't always lead to psi A, psi B. When, I don't know, always or not, but we can conclude if this is true, if this is true, then A and B are entangled. I'm using informatics a little bit writing. Beautiful. So love it so hard, so much. As Woody Allen said, I love it. Dan Keaton in Annie Hall? What was the name of the movie? I forgot. So, psi AB. Annie Hall, that was it. That was plus A plus B plus minus minus 2. So why do I put down 2 here? So if we have a qubit, right, it should be normalized. It is. If we have a joint qubit system, joint system, like this, then again it's square root of 2. It's not 2, it's square root of 2. Yeah, I made a mistake. So what is plus is 0 plus 1. And what is minus? Minus 1. And we want to simplify this. It's gonna be 0, 1 plus 1, 0, 1, 0 plus 1, plus 0, 1 minus 1, 0, 1 minus 1. Yeah, I'm right. So this is going to be 0, 0. Zero, 0 plus 0, 1 plus 1, 0 plus 1, 1 plus 0, 0 plus 1, 1 minus 0, 1 minus 1, 0. And this is going to be what? Radical 2, radical 2. No, it's going to be 2. Radical 2. So it's going to be 1, 1, 1, 1, 2, 2, 2, 2. So we need 2, 0, 0 plus 2, 1, 1 over 2 radical 2. So psi A B equals plus minus radical 2 equal to 0, 0 plus 1, 1 radical 2. EPR states entangled. And this cannot be written in this form. Simple measurements. Let us now examine how can we mathematically describe 34 minutes. It's fine. We're gonna go to more than that. Yeah, and also what I said here is like in 0, 0, this one. The amplitudes, square root of amplitudes, the square roots. This absolute value is squared of amplitudes, which is 1 over 2. Added to 1. And it should be normalized to. I'm fainting. Lack of energy. I'm in diet. That's the problem. Okay. I get to the measurements, quantum measurements. Beautiful. And I'm gonna make a pause and oh, expectation values, so beautiful. And then we're gonna go to what? I'm just saying what's gonna happen to keep me excited and energetic. Measuring multiple qubits after measuring, distinguishing quantum states. Unit transformation. Oh my god, that's so beautiful. Identity matrix, nice. Trivial. Unitary operation, very nice. Hadamard. Power matrices are unitary, yeah, of course. Bloch sphere, very great. Ingredients. State of the art. Then we're gonna finish with problems. Wow, amazing. EPR pair. All the chapter notes, the books that has been recommended, they're just like classical books. Griffiths, Nielsen Chuang, Gilbert Strang, linear algebra. Cheat sheets. Wow, you're a genius, man. That's so amazing. Love it. Then we're gonna go to the quantum tools on the first protocol. Density matrices. Their properties, that's great. I love it. I can't wait to get these two kind of things. Post-measurement states, partial trace, mathematical transmission, secure message transmission. That's amazing, man. But that's a lot of preparation to start chapter notes, density matrices. Quantum money.